Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to guide you through this one because we are taking a fascinating journey into the cosmos. Today, we're looking at an incredible region of space known as Caldwell 68, or NGC 6729. It's this stunning variable emission and reflection nebula nestled right at the border of the Coronae Australis and Sagittarius constellations. And let me tell you, this isn't just some pretty, static picture of a space cloud. We're about to uncover a totally dynamic, shifting, and deeply mysterious environment that really challenges our understanding of how stars are born.
So let's dive into this incredible paradox. Just picture this. You're looking up at the night sky, and you see a massive cloud of gas and dust. A structure so incredibly vast that it takes light years to cross. But then, you look back just a day later and notice it has completely changed its shape. For astronomers, this was the central mystery of a true celestial detective story. I mean, it seems physically impossible for something that gigantic to move that fast, right? So what exactly is going on in the dark corners of Caldwell 68?
To truly appreciate how wild this mystery is, we first need to anchor ourselves to the sheer scale of the universe. This dynamic light show is happening exactly 500 light-years away from Earth. That means the light we're capturing in our telescopes today actually left this nebula 500 years ago. Despite this vast, unimaginable distance, the events unfolding out there are so energetic and so massive that we can watch them happen quite literally overnight.
Let's lay down some foundational facts about this region. Caldwell 68 is what we call a fan-shaped variable emission and reflection nebula. But here's the thing, it doesn't shine all on its own. It's entirely powered by this powerhouse star named R Coronae Australis, or R Cray for short. Now, R Cray is a pre-main sequence star, which just means it's incredibly young and hasn't fully settled down yet. It basically acts like a massive cosmic floodlight, illuminating all the dust clouds that fan out toward the southeast.
Our understanding of this beautiful nebula has evolved so much over time. It was actually first discovered way back in 1861 by Johann Schmidt. But it wasn't until 1921 that the legendary astronomer Edwin Hubble visually noted some really obvious changes in the nebula's structure within a mere 24 hours. Fast forward to 1987, and astronomers Graham and Phillips used digital CCD detectors to observe and quantify these changes, linking them to cosmic shadows. Finally, by 2005, Nutter and his colleagues used high-tech submillimeter mapping to peer completely through the dust. We've literally gone from just looking at the glowing surface to essentially taking an X-ray of the cloud's heart.
Section 1. The 24-hour shapeshifter.
The idea that a cosmic structure could be a literal shapeshifter over a single Earth day is completely counterintuitive to the slow, eon-spanning timescale we normally associate with astronomy. But in the 1980s, the data proved that this was exactly what was happening. Just listen to the sheer shock and urgency in this observation from the 1987 Graham and Phillips paper. They state, measurable changes in the surface brightness of the reflection nebula associated with R Cray occur over intervals as short as 24 hours. Let that sink in for a second. A giant wall of cosmic dust, changing its brightness and structure essentially while the astronomers were sleeping.
Let's break down those 1984 observations to understand what's actually happening. In a span of just 23 days, that central star, R Cray, brightened by an astonishing 1.3 magnitudes. But as they watched, they saw bright and dark patches moving across the surrounding nebula at speeds approaching the speed of light. Now, the critical finding here was that these changes weren't because the central star itself was pulsating or physically spitting out new gas. Nope. Instead, these light and dark patches were the result of local, incredibly dense obscuring clouds blocking the star's light. Section 2. Casting cosmic shadows. So, the absolutely crucial point here is that we aren't seeing the nebula physically move. I mean, if a giant dust cloud were actually traveling that fast, the energy required would be catastrophic. Instead, we are seeing the effects of massive cosmic shadows sweeping across the face of the nebula. It's a total optical illusion on a galactic scale. To understand this, we have to grasp this brilliant concept called a light echo. Because the nebula acts like a giant mirror reflecting the light from our craft, the light takes time to travel from the star, hit the dust, and bounce toward our telescopes. The researchers noticed that the spectrum of the nebula matched the spectrum of the star perfectly, but with an observable time delay of 2 or 3 days. We are literally watching a delayed historical broadcast of the star's past behavior echoing off the distant dust.
I want you to visualize this with a simple, everyday analogy. Imagine R Cray is shining brilliantly, like a bare light bulb hanging in the center of a large, dark room. Now, picture dense clumps of dust, which is just leftover material from the star's formation, orbiting extremely close to that light bulb, practically fluttering right next to it like moths.
As those tiny moths orbit the bulb, they cast massive, sweeping shadows onto the distant walls of the room, which represents the outer nebula. Because the walls are so far away, a tiny movement near the bulb translates to a massive, super fast-moving shadow sweeping across the room. And that is exactly how Caldwell 68 changes shape in 24 hours. And this brilliantly illustrates a dividing line in how we study the universe. Traditional optical telescopes, which use visible light, reveal the glowing reflection nebula and those massive sweeping shadows. But to figure out where those dense, obscuring clumps of moth-like dust are coming from, we need different tools. Sub-millimeter telescopes can pierce right through the glaring optical light and all that thick dust to reveal the hidden, cold objects completely unseen by human eyes.
Section 3. X-raying the dust. By looking at different wavelengths of light, specifically using the scuba mapping data from the James Clerk Maxwell telescope in 2005, astronomers gave us an entirely new perspective on Caldwell 68. This sub-millimeter map is basically an X-ray vision superpower for astronomers. Where optical telescopes just see a wash of glowing gas and shadows, this data traces the densest, coldest dust in the molecular cloud. When you look at those deeply embedded concentrations, you're looking at hidden objects, protostars, and dense cores previously totally masked by the dark cloud's invisible light. We are peering directly into the stellar nursery.
Let's zoom right in to the brightest, most intense source in that map, an object designated SMM1. When viewed with this high-resolution data, SMM1 isn't just one massive blob of dust. It actually breaks apart into 3 distinct, separate components. This isn't just a single dark cloud casting shadows. This is a complex, active nursery of baby stars in different stages of being born.
Let's systematically categorize these hidden baby stars we've just uncovered. First up, we have SMM1A, which is a prestellar core. It's incredibly cold, just 11 to 15 Kelvin, and it completely lacks a central heating source, meaning the star hasn't even ignited yet. Next is SMM1B, a deeply embedded Class 0 protostar, basically a true baby star that has just started its gravitational collapse. Finally, we have SMM1C, a Class I protostar, which is a bit more evolved and is already putting out radio emissions. So right next to our central star, we have an entire family tree of stellar evolution. Now check out the scale of these objects when we look at their envelope mass. SMM1B and 1C, the more evolved protostars, are relatively small at 0.2 and 0.6 solar masses. But look at SMM1A. This cold, prestellar core is massive, harboring around 8.8 solar masses of raw material. That is a gigantic amount of pristine, freezing dust and gas just waiting in the darkness to gravitationally collapse and ignite into a brand new star.
Section 4. Echoes of our origins.
It is incredibly easy to look at all these charts and maps and forget what they truly represent. But we need to connect these distant, swirling dust storms directly back to ourselves. Because by studying the frantic, chaotic environment of Caldwell 68, we aren't just categorizing distant dust clouds. We are literally looking at our own history. Keep this number in your head, 5 billion. 5 billion years ago, our very own solar system looked exactly like this. We were once a chaotic, flickering, stellar nursery filled with dense clumps of dust orbiting a newly ignited sun, casting sweeping shadows across a massive dark cloud before finally settling down into the planets we know today.
I absolutely love this quote from the 1987 Graham and Phillips paper because it captures this sense of wonder perfectly. They wrote, "Close attention to regions such as this can be expected to provide insight into those circumstances which led to the formation some 5 billion years ago of the planetary system around our own sun. By looking 500 light-years away, we are effectively utilizing a time machine. We are observing the raw blueprint of our own creation."
From shape-shifting nebulae playing shadow puppets in the dark to freezing prestellar cores waiting to ignite, Caldwell 68 proves that the universe is immensely dynamic and full of hidden layers. So, I leave you with this thought. If we found an entire family of unborn stars hiding in the shadows of just one nebula, what other cosmic origins are hiding out there in the unseen universe waiting to be discovered? Thank you so much for joining me on this explainer. Keep looking up and keep questioning the shadows.